So thank you, Arnav and Pinaki, for this organizing this nice conference and also for the invitation. Okay, so this is what I'm going to talk about. So it will be clear as I go along. So it's basically I'm going to talk about how do you derive hydrodynamics starting from microscopics. So this is done. These are my collaborators. So Ritik and Soumya, these are students, and then Tridip is in TIFR and Abhishek is in ICTS, and this should appear soon. Okay. So as we are discussing during lunch, I think people have gotten bored of seeing this thing. Every meeting you go to, you see few slides of these ones. So this is what active matter is this, and you cannot start an active matter talk without one of these pictures. So active matter, if I want to just say simply, is a class of non-equilibrium systems. So where energy is injected at the microscopic scale, and so by this we drive these particles at the individual levels. Okay, and at the level of individual particles, these particles exhibit self-propelled motion, and often you see that if you put a large number of these self-propelled particles, they generate nice self-organized structures. Okay, so this kind of thing also not only in natural, and okay, again people have seen this in multiple talks. So this kind of self-propelled particle can be also realized artificially, and then again if you put all these things, they generate very nice structures. Okay, so if you want to learn about this, there are excellent reviews, but in fact it turns out that there are too many reviews in fact. So it says how the field is in fact growing, and so if you look at there, so apparently there are more than 600 reviews, and all this disk, the size of the disk basically represent number of reviews, fraction of reviews in that field, and there is in fact a meta review which reviews all these reviews, because there are so many reviews that you cannot keep track of these reviews. Okay. Yes.
I think we should now name it interactive.
Yes. So it okay. It's one sense, okay, there are, in one way you can say that there are too many people in the field, or also it's a field, basically it has gained lot of interest among a large section of community. Whatever people have been doing, they are just putting activity, and then that has creates another this thing. Okay. So now, but if you want to understand active matter, the collective properties of active matter, usually there are two routes. So one is you start with, you write down some hydrodynamic equations, and these are usually phenomenological equation. You basically start with, write down this equation based on some symmetry and conservation law, and basically you write down all the terms allowed by this symmetry and conservation laws. Okay, and so this is a top-down approach, and so usually you will have an equation like that. So you have this order parameter fields, and there will be some term which is like a passive term which you can derive from some kind of free energy functional, and there are some other terms which you cannot derive from a free energy functional. And okay, this is a lecture notes. If you are interested, you can look apart from these previous reviews. This is another one. You can just look at it basically like it's a nice lecture note, Deju's lecture note, and it just summarizes it. So the other approach is basically, okay, so you write down simple model, okay, and then you put large number of particles, and then you do simulations. Okay, and these models are fairly simple. You write down some local rules, and then, okay, for example, VSEC model, active Brownian particle, run and tumble particle, and then you put some local interaction, some kind of, depending on what you want to study, and then you do simulation. And so both these approaches turns out to be quite successful in understanding active matter. But usually if you want to, going from here to here is very hard. Okay, either you come from here or you do there, but starting with a microscopic model and deriving hydrodynamic systematically, it's a very challenging task. Okay, and so this is what I mean, this bottom-up approach. So basically start with a microscopic model, and then you arrive with the fluctuating hydrodynamic description of these few relevant order parameters in the system. Okay. So in this way of deriving, the parameters in the final theory are unambiguously defined, unlike this the hydrodynamics you write down from phenomenological let's say symmetry and conservation laws. Okay. But this one, as I say, it's much more challenging, and even like the simple characteristic of this many body phases like motility induced phase transition, where you don't even have this self-aligning interaction about this particle, it's very hard. Okay, and there are only a handful of cases where one can do this. Okay, so let me just briefly say what is this motility induced phase transition. I mean, people must have seen it again multiple times, but basically if you put these self-propelled particles together, so they spontaneously separate between a high density region and a low density region without even putting any attractive interaction between the particles. Okay, so without any attraction, so the system basically find a high density phase and a low density phase. Okay, so there are some reviews, you can look at it. Okay, so the minimal phenomenological model which describe this kind of motility induced phase transition is, which is called this active model B. So without this mu A, it is a model B, where basically this one chemical potential you can basically write down, derive from a free energy functional, and where free energy functional is something like that. Okay, and this active whatever chemical potential, so this is something you cannot derive from free energy, and with this minimal model actually you can see that if you just evolve this model, you see this separation of phases between the high density and a low density region. So phi is like the density parameter. Okay, but as I said, this, so of course you can write down this phenomenological model, but deriving this hydrodynamics starting from some microscopic model is very hard, and one of the model where you can derive this is this. So let me just take some time and explain this model. So you consider this on a ring, so it's on a lattice with a periodic boundary condition. Let's first take it for in one dimension. Okay, so there are few rules. So one is, okay, so this each particle, it diffuses with a rate d. So what it means that in a small time dt, so this particle is a plus particle, it goes to an empty site with a probability d times dt, capital D times dt, and if there is a, and then the whole goes to the other one, so when it particle moves there, the whole goes to the other, and if there are two, and this diffusion is symmetric, for example, this particle also can go to the left side with the same rate, d times delta t, and if there are two adjacent particles, they just exchange their position with the same probability d times delta t. So they exchange their position. Okay, this is part of this diffusive mode. So this is rule number one. So rule number two is, so you have these two kinds of particle, plus and minus. So plus particle hops to the right with a rate lambda by L, and minus particle hops to the left with a rate lambda by L. Okay, so there is exclusion, so a site cannot have more than one particle. Okay, so this is the hardcore exclusion, and then there is this tumbling where a plus particle can switch to minus particle with a rate gamma by L square. So these are these three rules. Okay, so in this one, so you can derive hydrodynamics for this model rigorously. Okay, so I am not going to go into how you derive, but you basically from this site variable which are I, which is like a integer, so you can go to a continuous variable x, okay, and you can similarly rescale your time, okay, and in this hydrodynamics space and time, so it's you can find out the equation of this sort, okay, where this rho is basically the total density and m is like a polarization or magnetization is basically the separation, the difference between these two densities. Okay. Yeah, you can see, because the thing is that, see, there is this del square, so it's x square here. So x square is of order 1, so this is d, this is where this term comes from. This term is 1 by x, so therefore you need another 1 by L here, so that it cancels. And that other term, basically there is no derivative. This tumbling term doesn't have derivative, this is kind of the tumbling term. So in order to scale basically 1 by L square from everywhere, so you need to basically scale in this fashion. Okay. So if you basically write down the microscopic motion and then you do this scaling, basically that L comes out, goes out of the theory basically. Yeah. Only if you do that.
Why did you have to put in by hand?
No. So now, so this is this another thing. So this is, so these people did it this one. So then later this Yarif Kafri and his collaborators, so this model, for this model, you can actually derive this fluctuating hydrodynamics exactly. So you don't put the noise by hand. And so this is for this very specific model where this diffusion, when there is no particle next to it, or this exchange, it happens at the same rate d. Okay. So for this model, this model can be mapped to this ABC exclusion model, and then if you use this known result for this ABC exclusion model, then you can write down the fluctuating hydrodynamics for this model. Okay. So two remarks now. So to derive this hydrodynamics, you need this exchange dynamics, which is a bit unphysical, because if you are thinking of like modeling this active particle, if the two particles are coming, they cannot just cross each other, right? But although unphysical, it's actually crucial for deriving this hydrodynamics. So without this exchange dynamic, you cannot derive this hydrodynamics for this model. Okay. So therefore, this is a necessary, this exchange dynamics was a necessary for deriving this hydrodynamics. So number 2, this specific mapping to this ABC model relies on this precise parameters that, like, okay, if the diffusion, when there is no particle and single particle diffusion, and the exchange, it happens with the same rate d. So if you make it d1 and d2, this mapping breaks down and you cannot derive this hydrodynamics. So it's a very specific model for which you can derive this hydrodynamics. Yeah. So rho plus is basically the density of plus particle, and rho minus is the density of minus particle.
Yeah, so it's the empirical density, right? So it's
the empirical density, yes. Yeah. So it's the coarse grain density basically when you go from the occupation numbers. Okay. So this is where we come in. Okay. So we propose a lattice model. So that's inspired by this previous model, but without this exchange dynamics, which we call unphysical exchange dynamics, because if you are thinking of these are actually active particles, they cannot actually cross each other, like if you are on the same lane. Okay. So it incorporates excluded volume in the sense that it incorporates this hardcore this thing, because even the other model there is exclusion, but then it can still go through each other, but here we strictly incorporate this. So in that sense, this is dynamics is a closer to a realistic dynamics of active matter, and it's a clean generalizable bottom-up approach. It doesn't rely on any fine-tuning of some parameters in this lattice model basically. So it can actually, for generic lattice gas model, basically you can use that and you can derive this hydrodynamics. Okay. So let me just define this model. So this model is defined in quasi one dimension. Okay. So let me, for simplicity, let me just define it in a two-legged ladder. Okay. So you have this ladder. Okay. So now what are the moves? So you have these two spaces as before. So there is this volume exclusion. Each side can have at most one particle. And okay, so there is some average density, rho 0, by which you just choose your initial density. Okay. So particle number is conserved basically. So now there is a bias diffusion. So if a plus particle, it diffuses to the right with this rate, okay, and diffuses to the left with this rate. So there is this minus sign and there is this plus sign. So it plus particle diffuses to the right with a higher rate than the left. Similarly, a minus particle diffuses to the left with a higher rate than to the right. Okay. So this, instead of writing this lambda and gamma, basically it's useful to write down in terms of this thing, but it's essentially the same. Okay, so this is one. Then tumbling. So tumbling is basically a plus particle can switch to a minus particle with a rate this tau p to the power minus 1. So tau p is like a persistence time. Okay. Then lane crossing. So there is dynamics where a particle from lane bottom lane can go to the top lane. So this happens with rate this 1 over tau x. Okay, so these are these three rules, and this dynamics mimics a self-propelled particle with persistence time tau p. Persistence time is basically the time at which this particle basically goes in one direction. Diffusivity LD square by tau p, and self-propulsion speed is LP by tau p. And here this LD and LP, these are dimensionless length, basically these are measured in terms of the lattice spacing. Okay. Sorry?
What is the two lane?
So you have two lanes. Basically this model is defined on a quasi one dimension. So you can in fact have multiple lanes, but okay, for simplicity let's say you have just two lanes. Okay.
Same question. So lane crossing means what? Actually, this.
No.
This,
This particle, they can either move on its lane, or it can go to the jump to the next lane, and again, it's it. Physically two lanes, and they are connected. So it's just a lattice, basically two ladder. I'll come back to that actually. That's the punchline. Yeah, I'll come back to that actually. Okay. So why do you need this? Okay. Okay. So you can have actually multiple lanes. 2 is not this thing, but okay, let's just do for the 2. That I'll come back to it. Yes. Yes. Yeah. So now, so to give a hydrodynamic description, so what you start with this occupation numbers. So each site can have n plus or n minus. So n plus is basically 1 or 0. So either the site can have a plus type of particle, minus type of particle, or empty, right? It cannot have both. So the occupation variable is basically defined as n plus minus, and ij simply means that I is along the one this thing, and j is the lane index. So this n plus and n minus can have these values because either this is 1, this is 0, or this is 0, this is 1, or both 0, basically empty. Okay. So now to give a hydrodynamic description, so these are at the lattice level. Okay. So now give a hydrodynamic description. So you basically you have to rescale both space and time, and you rescale space basically I by LD. So this becomes now, if LD is large, this x becomes a continuous variable. Time again you rescale with this, and now you take this LD, LP, and tau large. Okay, while keeping this diffusivity, and this is something called the Peclet number. So you keep this thing fixed. Okay, so these are your parameter. So this you keep fixed, and you take this is large. Okay, so if you do that, then for finite tau x, which is basically the lane crossing time, which is of course much smaller than this other time tau p. So in this case, what you can show is that the two lanes equilibrate faster. They equilibrate by the time in this hydrodynamic time scale. So when you go from this discrete variable to this continuum field, basically both lanes are described by the same coarse grain density. Okay, so at this level, basically you have now forgotten the lane. Okay, so either top or bottom, it has the same coarse grain density. Okay, yes.
With the lane crossing, aren't you just reinserting, Julia's?
So that happens effectively. You are doing that, but that happens at a much lower rate because Julia's thing, this exchange happens at a rate d, and here exchange happens at a rate 1 by L basically. So exchange happens at a much this thing. So this is point 1, and the point 2 is that okay, if your aim is to actually have a bottom-up approach where you start with some microscopic, then the microscopic model should be better true to the real system, right? So you cannot say that I have an effective microscopic model and then okay, I doing something else basically.
Sure.
Right? Yeah. So it effectively creates this lane cross this exchange, but that happens at a much smaller rate.
Sorry. So when you do the coarse graining, you make some kind of assumption that you have large number of I.
I'll come back to that actually. So let me just this thing. So I'll come back to this coarse grain, but like before that, so I don't know how much time I'm going to get. So let me just first give you the results, and then I'll come back how I do the coarse graining basically. Okay. So as I said that you have this rho plus and rho minus. Now at this level, basically this lane 1 and lane 2, you have forgotten about it. This basically, it is described by the same coarse grain field, and for that you can actually derive this fluctuating hydrodynamics equation exactly. Okay. So I'll come to, and it's independent of this fine tuning of these parameters basically. Okay. And so so it turns out that this equation for rho is same as the hydrodynamic equation what you get earlier, but this equation for this m is actually different from this other hydrodynamic equation what you have for m. Okay, and see this etas, so these are Gaussian noises, and this both this eta rho and eta m, these are comes from this conservative dynamics where this particle doesn't change, so that's why this comes as a derivative. These are these conservative noises, and then this noise comes from this tumbling basically. Okay, so now given this model, so you want to see how good is your hydrodynamic description basically. Okay, so in fact what you can do is you can take the microscopic model, do a simulation, okay, and then you take your hydrodynamic model and you do a simulation, and you evolve in time. So these are at various times. You start with some profile like that, and you see that these lines are hydrodynamic evolution of the hydrodynamic equation, and these points are the molecular simulation this thing, and they matches quite well. And then you see that okay, in some parameter ranges, finally it goes to a phase separated state where you have a high density region and you have a low density region. Okay, so this is for this your separate m, whatever the polarization or magnetization. So you start with something this circle one, and then okay, finally it goes to this whatever. So you see that your whatever the hydrodynamic description and this microscopic model, they matches exactly without any fine tuning of parameters basically. So these parameters are whatever the parameters of the microscopic model, and that microscopic model parameters define the parameters of the hydrodynamic model. So there is no arbitrary parameters in this model. Okay. So now, so you want to see, okay, so given this hydrodynamics, so you want to see, okay, so you see that there is those equations, so there is a solution which is, if you have a constant rho, constant density and zero polarization, that's a solution of this hydrodynamic equation without the noise. So it's a noiseless hydrodynamic equation, that's a solution. So you want to ask whether that solution is stable or not. So this is the homogeneous solution, and you see that if you just do a linear stability, so you see that that solution is stable within that range. So that means basically, so basically this is unstable within that blue line. So in this regime, the homogeneous solution is linearly unstable. So therefore, in this region, the system separated to a low density and a high density phase. So on the other hand, you can also derive the binodal. So the binodal says that basically suppose you have suppose the system separates into two phases, a high density phase and low density phase. So which are the densities of this thing? So you see that, okay, so given a Peclet number for a given rho, so it gives these two densities, okay, and again you see that, okay, see binodal curve, you derive whatever you can derive theoretically that matches extremely well with a simulation of the microscopic model, okay, and then you can see that you can in fact look at the distribution of the densities within the microscopic model, and you see that, okay, as you expect that this is a separated space, so you have this whatever the bimodal distribution, so where these are these two densities basically. On the other hand, in this homogeneous phase, so you have only one density, okay. Third line, yes, I'm going to come to the third line, okay. So there is a third line, so I'll just come back to the third line this thing, okay. So now in fact, you can see that, okay, if I just take the, so in the previous one I was showing that, okay, the microscopic and the macroscopic matches this thing, but in fact you can actually see this, so this student has made a nice movie, so I think somehow, okay. Okay, so it's supposed to work, but I don't know how it, okay. Okay, so okay, it's working, something, okay, so, yeah. So you see that actually if you start with something profile and then finally this goes to this separator. So this is this outside this binodal where it goes to the homogeneous state, and this is inside this pinodal which goes to this phase separated state, and these lines are basically the evolution of the hydrodynamic equation, noiseless hydrodynamic equation, and these points are basically the molecular this simulation of the microscopic model, and they follow nicely, okay. So you can also compute the 2-point correlation function for this model, and so for the 2-point correlation function, starting with this fluctuating hydrodynamics, basically you compute these 2-point correlations between density or density, whatever polarization or polarization. Okay, so this, okay, I have not given you the analytical expression, but you can actually find this in the homogeneous regime. You can find this expression exactly. Okay. And so and then, okay, this basically has this exponential decays. Okay. Okay. So higher dimensions. So this model you can actually straightforwardly extend to higher dimensions. So there, of course, multiple ways you can actually extend to higher dimension. One way is, of course, you can just take that number of lane to be very large and you just keep the same dynamics basically. And this lane crossing time, basically now you take it to be this one. So it's basically with the same as the diffusion time scale, this thing basically. Okay. And then in this case, again, the noiseless hydrodynamics, what you derive is basically the same as the 1D hydrodynamics equation I have derived basically. Okay. So if you just take the lane to be large, so then because it's essentially active in one direction, so you get the same noiseless hydrodynamics. But you can also have a isotropic generalization basically where instead of this lane crossing, okay, you have a lattice and then, okay, so there are now 2D species and basically that defines these various directions. And each species has a favorite direction to move to, so that goes with this rate, and then in the rest of the direction it goes with a lower rate, and then one species can tumble to any of these species basically with a rate this one. Okay. So in this case also you can actually follow the same thing and derive this hydrodynamic equation. So this hydrodynamic equation is, okay, it is slightly different. Okay, but you can.
I have a stupider question actually.
Yeah.
Which is how do you even get any binodals or spinodal from the Monte Carlo simulation in 1D? Because you don't have a phase transition in 1D, I would think.
So it's quasi 1D. So that's why it's very important, quasi 1D. Right? Yeah. Yeah. Okay. So now, of course, both this kind of model, you can see that, okay, you start with something and then it separates. So this is this where you take the lane to large and then, okay, you see that, okay, this is basically given by this 1D hydrodynamics, this thing, and there, okay, you have another hydrodynamics equation, okay. So in fact, I think you can see basically if you start with some this state and then finally it basically goes to this phase separated state, okay. Yeah. So this is the advantage of working with students because they like generating these nice pictures basically, yes. Okay, so how do you derive this hydrodynamics? So it's not possible for me to actually go to the whole derivation, but let me just give you a sketch. So as I say, so initially you describe in terms of these occupation variables, okay, so these are this n, okay, and now you write down what is this propagator, or it says basically starting with some n0, so these are these vectors basically initial occupation. How do you go to this final nt at some time t, okay, so this again is basically the vector for the whole system, okay, so these are the occupation variable. So this you can basically write down this given this microscopic rule. So you can write down this formally you can basically express, okay, in terms of some action basically, okay. So then you go to this continuous variable and then so these are this hydrodynamic variable and then from there, okay, you can either write a rho plus rho minus or you can write in terms of rho and m, okay. And when you go through this one, so what you find is that, okay, you will have some action like that with something like that, where Hamiltonian, okay, will be given something like that, okay. So don't worry about, okay, the exact expression of the Hamiltonian, but basically you start with the microscopic, and then, okay, you have an assumption of, okay, local equilibrium, this thing, and then, okay, you just go through this. So these are this procedure people have earlier used for this other processes, basically. Yeah, there's a question somewhere? No. Yeah.
The previous slide, why do we have this voids in this MIPS in the right side?
That's a good question, and in fact you get it, and apparently I was told that even in some simulations or experimental systems, apparently you see this void. So, but see this, whatever the your binodal or this whatever this thing, they do not exclude. It just says that you have a two regions, one is a high density region and you have a low density region. It does not say that you can have void or you cannot have void, but apparently there are systems where you have seen this kind of structures actually.
No, but that depends on, so when you eliminate the M, right, and write an equation for just the rho, is the rho dynamics AMP or AMP plus? Because you have void.
See, this is just microscopic evolution. You just take the microscopic model and what it gives, whatever it gives, right? So now is a question of if you want to write down the hydrodynamics, it should reproduce this.
So in the continuum level,
Yeah.
if you have AMB plus, not AMB,
Yeah.
then you do expect voids.
Yeah.
And that's because you have microphase separation and not phase separation in that model. Whereas
No, these are not microphase separation. I'm going to come. This is not microphase separation. These voids are not micro. These are macro voids.
but these are bubbles, right? I mean,
These voids are not micro voids.
but
Yeah, yeah. Huh?
the plus is an
This
extra.
is a simulation. Yeah.
It's an extra term in the equation of.
Microscopic simulation, but this is at the macro scale.
No, I think this is more like microphase separation.
Why do you call it as microphase separation?
A local gradient.
This is you are seeing at the macro scale.
No, AMB plus gives you.
You can have, see, you can even have a,
It's not a gradient of.
see, nobody says that you can, the MIPS has to be one big cluster, no? I mean, you can have, I mean, this is what it gives, the simulation. Now, you can have or you cannot have means what? This is what, right?
Okay.
I mean, you do the simulation, you do the thing, this is what you get, right? I mean, now,
Let's just agree the system is not devoid of voids.
yes. Yes. So now, okay. Okay. So now, okay, given this whatever horrible Hamiltonian, so okay, so if you look at a Gaussian approximation in M, so okay, you have a slightly nicer looking Hamiltonian, and for this, okay, so these guys are this conserved current and this is this not conserved current, so you can basically, okay, this expression becomes nicer, and so in this case, basically, so the corresponding hydrodynamics equations are basically given by this, okay. So in some sense, so if you start with this hydrodynamics equation, and if you go through this Martin-Cizier formalism, so you end up with this axon what I have just shown before. Okay. So now let's come back to, yeah.
You went from the action to this.
Yeah, axon. I mean, so given this axon, the corresponding stochastic equations are these basically, right? Or if you start with this stochastic equation, you go to that axon. Exactly. So these are unique mapping basically. Either you go this way or the other way. Okay.
Sanjeev, 5 minutes.
Okay, I will be done. Yes. So now, why do I need the ladder, right? So in fact, if you take 1D model of this one, okay, and you just follow the same procedure, okay, you just naively follow the procedure, you end up with the same hydrodynamics equation, okay. So the naive following the procedure will give you the same hydrodynamic equation as this quasi 1D ladder, but it turns out that this hydrodynamic equation, they do not describe the evolution of the microscopic model. For example, if this in the microscopic, so you saw that this hydrodynamic equations actually supports MIPS, so it gives the MIPS solution, right? But this, if you do a simulation, okay, you don't see MIPS in simulation, or if you start with a phase separated state, it actually breaks down, okay? It takes long time to break down, but basically that state is not supported. So not only that, so if you actually start with, this is what I want to say, so if you basically start with a phase separated state, these points are microscopic and these lines are hydrodynamic, evolution of the hydrodynamic equation, and you will evolve them together, and these are precise this thing because we know how to go from the micro parameters to the macro parameter exactly. So you see that they don't follow, these evolutions are different, so this hydrodynamic evolution and the micro evolution, they don't follow. The same thing you do for this quasi 1D one, they micro and the hydrodynamics this thing, they follow precisely. So it says that this, no, it says that whatever the hydrodynamics equation you have written down, these are not valid hydrodynamics equation in one dimension. Okay, so that's what. So in fact, you can see if you take this hydrodynamic equation and fluctuating hydrodynamic equation, and then you compute the correlation functions of this density, they do not describe it. Okay, so in fact you can. So what is the reason for that? Okay, so what happens is that if you look at this quasi one dimensions, okay, so you see that actually there is a lot of activities going on, right? So this, the system mixes, okay. So locally the system equilibrates. So it is, you can have basically this Bernoulli product measure locally. On the other hand, for this strictly 1D model, so these are what I call it microclusters basically, okay. So particle aggregates, but they aggregate at the level of micro level, 2 particle, 3 particle, they will aggregate. And this one, because, see, if you take this system in 1D, this flipping happens at a much slower rate, right, going from plus to minus and minus, so that happens at a much slower rate. And at that time scale, the system cannot mix, that retains the order. If you have some 5 plus particle here, 6 minus particle here, some 3 plus particle, that order retains, so it actually the system cannot mix, okay. And because it cannot mix, basically it does not have this, so magnetization, for example, or this polarization, it cannot equilibrate basically, okay. It's a conserved this thing for this, and that you can actually even see, like if you actually compute the density profile, okay. So density profile is easy to compute because, okay, given a global density rho, post-grain density rho, you can write down this whatever the box density, just a binomial distribution, and then if you take the Starling approximation, which gives you this, yes.
That's right.
So that's why you need this this thing, okay. And this is in fact consistent because many other studies they have found that actually in one dimensions you cannot have MIPS basically, right? Yeah. So the reason you found this in Julia-Trier model, because you had this exchange, this thing and that this thing, okay. So you see that, okay, this, so at low Peclet number, so this is in the homogeneous regime. So in the low Peclet number, of course, this hydrodynamics and this microscopic this thing, so they seem to describe, because, okay, at low density, it's almost like a low Peclet number, you can think of it like almost like equilibrium, because particle just don't go and basically get stuck to that. But if you take this high Peclet number, you see that actually your density profile, what you get from the microscopic simulation and whatever your theory gives, they differ very much. As opposed to if you look at the quasi one dimension, it explains extremely well. Okay, so there is some little bit of discrepancy here, but this is because, okay, so this is a finite size system, and you assume that, okay, your MIPS is a clean MIPS basically, but then, okay, you have a boundary, and, okay, in the boundary, if you don't take care of it, this thing. Okay, so to conclude, basically, okay, so we have proposed a minimal model of interacting particles with excluded volume interaction and hardcore this thing condition. So for this model, actually, you can actually derive this hydrodynamics using a bottom-up approach, and this system exhibit MIPS this thing at the macroscopic level in quasi 1D or higher dimensions, and then, okay, Monte Carlo simulation and hydrodynamic description matches exactly without any fine tuning. There is no arbitrary parameters in the model, and then this procedure, whatever we have done, it's generalizable basically. You can take any lattice model, and if there is an equilibration at this microscopic time scale, basically you can derive this hydrodynamics using the same procedure basically. Yeah. Okay, so I'll just stop here.
Thank you for a beautiful talk. I want to check what is eta f. So you have introduced some quantity
Yes.
subscript to f.
Yes.
So I missed your explanation.
Yes, yes. I think this one.
Yeah, for example, last term.
Yeah. So this noise is coming from because plus particle is switching from the plus going to minus and minus going to plus. So this is basically the fluctuation of this m variable because of this switching.
Change of the variable.
Yeah. So there is a fluctuation because of this tumbling basically. Yes.
Tumbling
Yes.
down.
Yes.
Okay, thank you.
Yes. Yeah. So in fact, it's basically a Poisson process, and okay, in the bulk, if you take the Poisson process, and then okay, this is just a Gaussian approximation of the Poisson process.
I'm intrigued by the beautiful agreement between your theory and the Monte Carlo simulation.
Yes.
Did you monitor the rectilinear diameter, how it vanishes when when you have the coexistence? So you have two branches. So when you look at the distance between, for a particular Peckley number, distance between two values, and how does it vanish when you go to the apex? Does it have a critical exponent?
Yes. Oh, sorry. So I think okay.
What is the value of that one?
Yeah. So that is what. Okay, let me just come to that. That also reminds me this.
Yeah, there.
Question. Yeah. No. That also reminds me this dashed line. Actually, I was supposed to explain.
Yeah. Also, I like to know whether there is a critical exponent to that one.
Yeah.
What is that?
Exactly. So now the point is that okay. So as I said that this is the spinodal which says okay inside this system is linearly unstable. Okay. This is binodal. It says that okay if I have two densities basically it can it separates one density will be this and one density will be that. And in between this, it is a metastable region basically, in the sense that in principle, if I take any density here, it can split into two densities. But that depends on whether you are starting with already a separated state or a homogeneous state. And I think if you use noise, basically it will finally go to the homogeneous state. And this dashed line is the one where this correlation functions what we computed from the linear stability, from the fluctuating hydrodynamics up to a linear order, that diverges at that line. Okay. So now near that line actually we don't have a very good description. Okay. So now to answer your question, we need to do more basically. So we don't have a very good handle as this closes there, because in that case, okay, so I think we need to, there are two things, okay, we probably need to go beyond this Gaussian noise, this thing, and the other thing is you have to basically solve probably the full hydrodynamic equation and not just, yeah, so we do not know what is the critical exponent around that actually, yeah, but maybe we can discuss if you have any idea.
I can understand from simulation, I know it's very difficult to do.
Yes.
But from your theory, you should be able to make a prediction of what that exponent could be.
But these are very nonlinear equations, so I don't know how, I mean, these are nonlinear equations.
I got it. You got to do renormalization.
Exactly. So that's something we have in the plate, but okay, it's like a long, okay, Satya.
Yeah, so, okay, I have a couple of questions. One thing is that, can you also develop something like Kawasaki-Dean equation for these kind of things, like what we do using interacting particle systems?
Yes.
For passive particles?
Yes.
Is there an active version of it? And
in principle,
does it sort of match with this kind of hydrodynamics?
Yes, we have not done it, but in principle it is possible, but you have to describe at the lattice level basically. Not in the continuum. Going from continuum is continuum to hydrodynamic in this way is difficult, but going from the lattice, so if you define an equivalent lattice model with interaction, it should be possible basically to do that. Yeah, but we have not, we have not looked at it actually, yes.
The other question is a general question that, I mean, okay, I understand it's hydrodynamics, but usually often sometimes, you know, when you, why, I mean, you can ask, you know, why does this equation close onto itself in two fields, rho and m? Because typically, like often when you go from lattice model to continuum model, 1-point function might include 2-point function, 2-point will involve 3-point.
Yeah, exactly.
So BBGQI hierarchy type of thing.
Exactly.
But here somehow rho and m
So,
closes onto itself.
yeah, because I think this, because of this dynamics, they locally equilibrate, and in this case, basically, it's kind of like a Bernoulli product measure locally, basically, yeah.
Right, so,
I mean, in the sense that if you just do a naive hydrodynamics, okay, this term, this usually comes from some Ni times 1 minus Nj, and then it's basically like a product measure locally. But that we do not do at the microscopic level, but we do it at the coarse grain level, basically.
no, but because if you look at the normal like symmetric exclusion process and so on, so there you can actually see that, you know, it does closes up.
Yeah, because it has a Bernoulli product measure, symmetric exclusion, basically, yes.
But then there's an underlying symmetry to the problem or something that makes it look.
Yeah, I mean, well, I mean, so.
I mean, here, this model, see,
I mean, 2-point function might close out to 2-point itself.
yeah.
But 3 and 4-point may not. I mean,
Yeah. So each species here is basically a WASEP, basically. Yes.
What is the meaning of local equilibrium? I thought the systems are inherently out of equilibrium.
No, in the sense that you can define this coarse grain density, right, locally, and within that you can, so okay, so if you just forget this guys, for the time being noise.
For example, in a gas or something, when you assume local equilibrium, you assume a local equation of state.
Local temperature, let's say. Yes.
Local pressure and local.
Yeah.
But here, what is the equivalent of that? That is the.
No, the measure for the profile, right? You can locally define a measure which is basically, you can ask, okay, what is the, okay, so in the sense, what is the probability of having a plus particle there, okay? So that probability is basically rho plus locally, because, okay, that density we have defined in some range, and that's a slowly varying variable. So you can basically draw that Ni equal to +1 with rho plus and 0 with 1 minus rho plus, basically, right? Yes.
But does it, sorry, but does it work for generic systems, or only after comparing with simulation you can check whether this approximation is, what is the,
So the thing is that if you have this whatever local equilibrium, so then it will work, but now a priori it is not very easy to see, because these are not rigorous mathematical derivations in the right. I have not rigorously proved that this system has local product measure or something like that, right? So then in that case, okay, I mean, it's based on physical arguments, basically, okay, in one case, okay, the argument is basically that, okay, you have these two species, both are like this WASEP moving in opposite direction, right? And if you did not have this, so WASEP is basically weakly asymmetric exclusion process, but if you didn't have this flipping, going plus to minus, they're stuck actually, the system, right? And this order cannot change, okay? So therefore, this doesn't have this local whatever equilibrium in some sense, right? Although each species has a Bernoulli product measure, but this will not have basically, yeah. So I think in that vaguely, yeah.
Yeah, I guess I'm sort of, again, so the mathematical technique from coming from that, the action, where are you assume, is there an assumption of local, that's where I'm sort of.
Yeah, so this is basically, yeah, so this is.
Something that then fails in the 1D.
Yeah, so this is basically you do while going from here to here. So you have this microscopic this thing, and then from there basically you are describing in terms of a coarse grain density, right? So at this stage basically, yeah.
Okay.
Yeah. So usually, okay, so when you go from this micro to this macro, okay, there is also a, whatever this entropy term, but here, okay, entropy term is not very relevant, this thing, okay, it's a subleading this thing. But basically at this level you have this thing, okay. But you can blindly follow these ones, okay, if you can just blindly write it down, okay, and then you will arrive at the same equation. That's what actually initially we did. We'll just take the 1D model and then, okay, you arrive at this equation. And then you see that actually it does not describe this.
Yeah, but I guess as the question is, do you know where it?
Yeah, it's just basically from this microscopic axon to when you go to this macroscopic axon, this is basically at this scale, basically. Yes. Yeah.
If there are no further questions.
So, first question, which is that, the fact that you don't have microphase, phase separation in 1D is not a surprise, right?
It is not a surprise.
In the sense that even Ising model in 1D,
Yeah, I mean,
phase transition, but if you write down model A, you think that you have.
yeah, it's not a surprise, yes.
And as for Muthu's question about, the exponents, you can indeed do an RG calculation with those nonlinearities in A, B or A, B plus. I think I've forgotten the upper critical dimension, but it's fairly low. So in any reasonable dimension, it's the equilibrium model B exponents. So Z is 3. The chi is half and Z is 3.
Yeah, so here, okay, at this stage, basically our first aim was to, can you go from this micro to a macro description, and which is, okay, usually like there are very few examples, because either you write down this hydrodynamics or you write down this microscopic model, but there is no connection usually, like, okay, you just, okay, appeal to some symmetry and cause. Yeah, exactly. Yeah, exactly. So, no, in fact, people often get that noise term wrong because, yeah, because this noise term is in fact quite, yeah, if you see this, yeah, I mean, not here, somewhere there, I had this one. Yeah, these guys. This is quite non-trivial, basically. Yeah, you cannot just guess it, basically, this thing, right? I mean, yes. Yeah.
Any further questions, comments?
Yes, John.
So if you do the doppelity calculation, would you not get what the noise should look like?
This is what similar to doppelity, but okay, whatever you call it. This is basically similar procedure, right?
Yeah, but when you get the action, like, wouldn't you get the?
No. The question is, if you write down the phenomenological hydrodynamic equation, right, which is most based on some symmetry and conservation laws, we don't have any way to, I mean, guess what is the noise, this thing, basically, right? So therefore, you need to go through this microscopic or axon formalism, whatever this thing, and that gives you the this thing. Right? Yeah. Yes. Yeah, equilibrium is easy because, yeah, I mean, because they are, yeah, exactly.